Hey Algebra 2 friends, we're going to be talking about adding and subtracting rational expressions. So there is no vocabulary for this particular section, but you know what we're going to be doing? We're going to be actually adding and subtracting fractions that look crazy. That's kind of what's happening. And if you remember, when you add and subtract fractions, you need to make sure you have the least common denominator, or sometimes it's the least common multiple. So what we're going to do here in this first example is to practice finding the LCM. And so what I like to do, and I've mentioned this before, is you know that the least common multiple must contain each of these numbers. So one thing we can do is factor each of the values to see what all the factors that are within each number. So here I've factored them down into their prime factorization. And what I do is I can literally just take one number. Let's take this first one, the 18r squared s to the fifth. And that's going to be written as 3 squared times 2 times r squared s to the fifth. So I already know that this new part of my LCM has everything that 18r squared s to the fifth needs. But now I need to see if I can contain 24r to the third s times t to the second. So what I start doing is I start adding just enough to make sure that 24 can fit in there. So I know that 24 requires 3 2's, so 2 to the third power. So I obviously need to add 2 more 2's in there, right? 24 requires a 3. We already have that, so I don't need that to make 24. So 24 is in here. The next thing I'm going to do is get r to the third power. I just need one more r to have r to the third power. S to the fifth already contains s. And finally, I just need t squared. So now I know that this number can contain 18r squared s to the fifth and 25r to the third s times t to the second. Woo, let me make sure that I can get this last number in there. So is there a 3? Yes, there's at least one 3. Is there a 5? There isn't. So I need to throw a 5 into the mix. Now I know that 15 is covered. S to the third power is covered by s to the fifth, and t is covered by t squared. So now I'm going to multiply this out and see what is my least common multiple for these three terms. So we end up with 360 when I multiply all the numbers together, and then I just collect my variables and I have r to the third, s to the fifth, and t to the second. All right, let's go ahead and try another example. Sometimes we'll have to find the LCM of polynomials, and just like we did with that last problem where we had to factor each of the terms, we're going to factor each of these polynomials. Let's do that first. So after a quick moment of factoring, I got that this polynomial factors in this way, and this polynomial factors in this way. So I'm going to start off like I did before. I'm going to start off with one of the terms, or one of the factors. So I know that this polynomial would definitely divide evenly into this. So this is definitely a common multiple because it is itself. But now I'm going to see what I need to add. I need p plus 3 twice. I need 2 factors of p plus 3. And I don't have that. I only have 1 factor of p plus 3. So in order to get that, I'm going to have to add the next one in there. So now instead of just p plus 3, it's p plus 3 squared. And so now you can see that each of these polynomials can divide evenly into this new polynomial combination, which would be the least common multiple. So here we are getting to the heart of the matter. In order to add 2 fractions, we know we need a common denominator, and so I'm going to get started with that. Similarly, I'm going to say, okay, this is 3 times 5, y squared, and let's just say this is 3 times 6, x times y. And I can see enough of the factors to see what I'm going to need. So I know I need a 3 and a 5 and a y squared, but so I'm going to use that in both of the new denominators, but to that I also need to make sure that there's a 6 involved, and there is no 6, so I'm going to throw a 6 in the mix. And then I also need to make sure that there's an x. And so now I know that both of my original denominators can divide evenly into this new one. And so let me neaten this up a little bit. And once simplified, we see that our denominator, or our least common denominator, would be 90y squared x. And so with that, we need to figure out, okay, what did we multiply this denominator by in order to make it into the new one? Well, clearly the 6 was added and the x was added. So I'm going to multiply this numerator by 6x, and when I do that, I get 42x squared. Over here, what did I multiply this original denominator by in order to get this new one here? Well, we already had the 3 and the 6 and the x and the y, but we added a 5 and a y. So I'm going to multiply 5y here. And so when I do that, I get 5y squared. Joining like terms together is not possible in this case because the numerators aren't exactly like terms, but I can join these fractions together. So in that way, I'm joining stuff together that's alike because they have the same denominator. And so I get 42x squared plus 5y squared, all of that over 90. I could probably do some factoring. No, I can't. I thought I could factor out of a 42, but I can't. That's not a 40, it's a 42. So I can't, so I'm gonna leave it at this. So here in example 4, we're going to do the same thing, making sure to factor the denominators completely. We do that so we can see exactly what is in the denominator. So now we need to figure out, okay, what do we need to make a common denominator? And when I look at this, I like to start off with one of them. So I've got 4w minus 4. Let's start off with that because I know that denominator needs to divide evenly into my new one. So with that done, I see what do I need to add in order for 2 times w minus 4 to divide in evenly. W minus 4 is there and 2 is actually there in the 4. So I don't need to create a new denominator because this denominator happens to be the least common denominator for both of them, which is awesome. So that means my numerator does not change. I'm going to leave my numerator the same here. Then I have to consider what did I multiply this by in order to get this, and that's a 2. So that 2 will appear in my numerator. Now I'm going to multiply through. Now here's the thing that I need you to be aware of. This negative is kind of attached to this side of the problem in that whether the 2 was here or not, we would have to distribute the negative through. But now that the 2 is here, we're going to look at this as a negative 2. So watch what happens. In both of the fractions are going to be joined together because they have a common denominator. So I can write them all over one fraction bar. I have w plus 12, watch this, minus 2w, that's me distributing through, minus 8. Joining like terms together, I end up with a minus w, with the w's there, and then a plus 4. And if you remember from the last section that we worked on, when we see stuff like this, sometimes I call it flip-floppery, when you see that this number, if I factored out a -1, basically we'd have the same factor here. So we'd have the same factor and we can cancel. So that's what we're going to do. We're going to cancel this, recognizing that we'll get a -1 out of it. So I'm going to just draw an arrow here. My final answer is -1/4. Hopefully that makes sense, all right? So we were moving into this idea of a complex fraction, and our text does a couple of interesting things to solve complex fractions. When we get together live, I'd like to talk to you about complex fractions a little bit more if you have any questions, but also just because I mentioned before, there's a lot of different ways to solve them. One way I like to solve these guys, and it's not really in the text, is to hit it with a gourmet one. So what I do is I look at all of the denominators and I try to see what would be the greatest common or the least common denominator. And I hope you all can see that it would be x times y because this denominator is 1, this is x, this is x, this is y. What you do with that is you make a ginormous gourmet one. It's not really ginormous, but what we're going to do is we're going to multiply through the top and bottom of this complex fraction with xy. And what that's going to do is make our complex fraction a lot less complex. So I'm going to treat this like a distributive property situation, and I'm going to do exactly what you think. I'm going to multiply through. So think about it. X times y over 1 or times 1x is going to leave me with just y. Right? Because the x's will cancel out. X times y times 1 over y is going to leave me with just x. Nice, right? Watch what happens down here. X times y times 1 is going to leave me with xy, not too bad. And x times y times 1 over x, just like before, left me with plus y. And so this is a lot easier to deal with. At this point, I might want to think about, I would try to factor out if I could. I can factor out a y in the denominator and then I get x plus 1. But unfortunately, none of these factors cancel, so I'm kind of left with this. But wasn't that just a quick and dirty way of knocking this crazy looking fraction down? Remember how I made this crazy gourmet one? I looked at all of the fractions that are within my complex fraction and made sure I came up with a common denominator, or the least common multiple. And then when I did that, I made a 1 out of it, multiplied the top and bottom, and everything got straightened out really quickly. Let's try another example. So in this final example, we're going to use a complex fraction to solve a problem. So we're asked to find the slope of a line that passes through these 2 points. And if you remember, we've talked about it before. Slope, or m, sometimes we refer to it as m, the variable y sub 2 minus y sub 1 over x sub 2 minus x sub 1 is the ratio we use. And so what we'll do here is we will substitute right into that formula using each of these respective points as x sub 1, y sub 1, x sub 2, y sub 2. So here we are with this, all right? It's okay, we can handle it. We should figure out what we can do. And remember what we talked about last time, making a common denominator and using that common denominator to make a gourmet one. The common denominator here would be, well, 2 needs to be in there, p, and 3 and p. It would be 6p. I hope you can see that. So I'm going to multiply the top and bottom by 6p and watch what happens. All right, once I do that, okay, I wanted to move that and get some space. We're going to multiply this here, and this here, and this here, and this here. So look how nice this is. I end up with 18 minus 3p over 2p minus 12. And then I factor the 3 out, and I get 3 times 6 minus p and 2 times p minus 6. And I know you see it. We've got 2 factors factors that will cancel each other out and leave us with a -1. So my final answer is -3 over 2. I know that was a little weird, but I hope that it made sense. Let's talk again soon. Let me know if there's any questions about the gourmet one and trying to simplify some of these complex fractions. I look forward to talking to you guys soon. Take care.